Why did Richard Feynman say QED is so extraordinary? Quantum Electrodynamics, or QED, is one of the most important theories ever created by human beings. It explains how light, electricity, magnetism, and matter interact at the smallest level of reality, the level of atoms and subatomic particles. In simple words, QED is the mathematical language the universe uses to communicate. QED describes how particles, such as electrons, interact with particles of light called photons. Whenever light shines, a phone turns on, or electricity flows through a wire, QED is at work behind the scenes. But what truly shocked scientists, especially Richard Feynman, was not just what QED explains, it was how incredibly accurate it is.
Throughout history, humans have created many scientific theories to explain how the universe works. Some were revolutionary, some were extremely useful, but none were perfectly accurate. Most scientific theories are approximations. They work well, but only within limits. For example, a theory might be 90% correct, or in very good cases, 99% correct. Even Isaac Newton's laws, which ruled science for over 300 years, eventually failed at extreme speeds and tiny scales. Nature always revealed small errors. But quantum electrodynamics, QED, changed everything. Unmatched precision. QED does something no other theory in science has ever achieved. Its predictions match experimental results to 10 decimal places. That means if physicists calculate a value such as 1.0000000001, real-world measurements produce nearly the exact same number. The difference between theory and reality is smaller than 1 part in 10 billion. This level of accuracy is almost impossible to comprehend. To put it into perspective, if QED were a map of Earth, it would be accurate down to the width of a human hair. If QED predicted the distance from New York to Tokyo, it would be off by less than a millimeter. No other scientific theory has ever achieved anything remotely close to this. Humans and the universe agree. What shocked Richard Feynman most was not just the accuracy, but who was doing the calculation. On one side, humans using chalk, writing symbols on blackboards, manipulating abstract mathematics. On the other side, nature itself, using real electrons, real photons, real energy. Yet both arrived at the same numerical answers. This meant something extraordinary. The equations written by humans matched the calculations performed by the universe itself. Feynman described this agreement as the most accurate prediction in all of science. Nothing else, not chemistry, not biology, not relativity, comes close. Tested again and again. QED was not confirmed once. It has been tested thousands of times over decades. Scientists measured the magnetic moment of the electron, the interaction between light and matter, quantum fluctuations in empty space. Every time experiments became more precise, QED survived. When technology improved, QED did not fail. Instead, it became even more accurate. Each new decimal place confirmed the theory again. It is as if nature kept saying, yes, that number is correct. Why this is almost unbelievable. The universe is chaotic, complex, and constantly changing. Yet QED works with astonishing perfection. It describes invisible particles appearing and disappearing from empty space, interacting through forces we cannot see, and still produces exact numerical predictions. This suggests something deeply philosophical. Reality itself appears to follow mathematical rules with absolute precision, not approximately, not symbolically, but exactly. Even Feynman was uncomfortable. Despite helping create QED, Feynman admitted something unusual. He said, "It is difficult to believe that such a strange theory could be so accurate. The theory involves particles traveling backward in time, virtual particles popping in and out of existence, and probabilities rather than certainty. Yet somehow the math always works." Feynman believed this accuracy was almost unsettling, as if humans had briefly uncovered the source code of reality. Why this makes QED unique? QED is the most accurate theory in human history because its predictions match experiments to 10 decimal places. No other theory reaches this precision. Every improved measurement confirms it again. It connects abstract mathematics directly to physical reality. It is not merely correct, it is precisely correct beyond anything science had ever imagined possible. Science usually progresses by approximation. We expect theories to be replaced. We expect errors. But QED stands apart. It is so accurate that physicists do not ask whether it works, only why the universe allows such perfection. For the first time in history, humanity did not just describe nature, it matched it, digit for digit. And that is why quantum electrodynamics remains the most accurate theory ever created by the human mind.
One of the most astonishing things about quantum electrodynamics is not just its accuracy, but who is doing the calculation. On one side, we have humans. Physicists sit in rooms writing symbols on paper. They use chalk, equations, and abstract mathematics. On the other side, we have nature itself. Electrons move, photons are exchanged, energy flows through space. No paper, no formulas, no thinking. Yet somehow, both produce the exact same answer. When scientists calculate the behavior of particles using QED, they obtain a number. Then they perform the experiment in the real world, and the result matches, not approximately, but to 10 decimal places. This shocked Richard Feynman more than anything else, because it meant something extraordinary. The universe is performing the same calculations that humans write down mathematically. Nature does not know mathematics, and humans do not control nature. Yet the structure of our equations mirrors the structure of reality itself. It is as if the universe follows a hidden algorithm, and mathematics is the language used to describe it. Feynman found this deeply mysterious. How can marks on a blackboard predict the behavior of particles that exist billions of times smaller than an atom? Why does reality obey abstract symbols created by the human mind? No one truly knows. But QED proves one thing beyond doubt. When humans calculate carefully enough, their equations and the universe arrive at the same result, digit for digit. That is why QED is not just accurate, it reveals something profound. Human mathematics is not separate from nature. It is woven into the fabric of the universe itself. And that realization is what truly amazed Richard Feynman.
Before quantum electrodynamics, humans believed the universe worked in a simple, logical way. They believed that every event must have one clear cause and one definite outcome. If you throw a ball, it follows one path. If you push something, it moves in one direction. Reality seemed predictable, deterministic. But QED revealed something shocking. At the quantum level, the universe does not behave with certainty. It behaves with probability. Not one path, every possible path. According to QED, a particle such as an electron does not travel along a single path from point A to point B. Instead, something unbelievable happens. The electron explores every possible path at the same time. Some paths are straight, some are curved, some loop wildly, some even go backward in time. Paths that seem impossible to us are still included. Richard Feynman described this idea using what is now called the path integral. In his words, nature behaves as if it is calculating all possibilities. How reality chooses. The universe does not choose one path directly. Instead, each possible path contributes a probability. Some paths reinforce each other. Some cancel each other out. When all possibilities are combined mathematically, one outcome becomes most likely. That outcome is what we observe as reality. So nature does not say, "This must happen." It says, "This is the most probable thing to happen." A radical idea. This was completely opposite to classical physics. In classical thinking, same cause, same result, always. In quantum reality, same cause, many possible outcomes. The universe does not run like a machine. It runs like a probability engine. Certainty disappears. Only likelihood remains. Why this changed everything? QED showed that uncertainty is not due to poor measurement. It is not because we lack information. Uncertainty is built into reality itself. At the deepest level of existence, particles do not have fixed paths. Events are not predetermined. Outcomes exist only as probabilities. Reality becomes definite only when it happens. Until then, the universe exists as possibilities. What Feynman found so astonishing. Feynman was amazed that such a strange idea could produce such perfect accuracy. A theory based on uncertainty, randomness, and invisible paths should not work so well, yet QED predicts reality with unmatched precision. This taught physicists something profound. The universe is not governed by certainty, but by mathematical probability. Final insight. QED did not just change physics, it changed our understanding of reality itself. It revealed that the world is not fixed in advance. It is constantly being chosen from countless possibilities. What we experience as reality is simply the outcome that probability allows. The universe does not decide what must happen. It decides what can happen and how likely it is. And that is one of the deepest truths QED has ever revealed.
Quantum electrodynamics is one of the most accurate theories ever created. But there was one problem. The mathematics behind it was extremely complex. So complex that only a few physicists in the world could use it. Even brilliant scientists struggled to calculate quantum interactions. Then, Richard Feynman changed everything. Instead of using long, impossible equations, Feynman created something revolutionary: simple drawings. These drawings became known as Feynman diagrams. At first glance, they look almost too simple. A straight line represents an electron. A wavy line represents a photon. When an electron emits light, the lines connect. When light is absorbed, the meets again. But these pictures are not illustrations. They are mathematics in visual form. Each diagram represents a real quantum interaction. An electron emits a photon. The photon travels through space. Another electron absorbs it. Particles can appear, disappear, and re-emerge from empty space. What looks like science fiction is actually how nature behaves at the quantum level. The brilliance of Feynman diagrams is this: every diagram corresponds to a precise mathematical term. Physicists simply draw all possible diagrams, calculate their values, and add them together. Suddenly, calculations that once took years could be done in days. These diagrams transformed physics. They allowed scientists to calculate quantum processes with incredible accuracy, accurate to 10 decimal places. Because of them, QED became usable, testable, and unbelievably precise. Feynman diagrams did not just help physicists understand the universe, they made modern technology possible. Without them, we would not have semiconductors, lasers, microchips, computers, and modern electronics. What makes this achievement even more remarkable is its simplicity. Feynman turned the deepest laws of reality into drawings that fit on a chalkboard. Pictures that look childlike, yet describe the behavior of the universe itself. That is why Feynman diagrams are called the pictures that transformed the world.
They proved that sometimes a simple idea can unlock the most complex reality imaginable.
Quantum electrodynamics is not just a theory found in physics textbooks. It is the invisible foundation of the modern world. Nearly every advanced technology we use today depends on QED being correct. At its core, QED explains how electrons and light behave, and modern technology is built entirely on controlling electrons and photons. Smartphones. Inside every smartphone are billions of transistors made from semiconductors. These transistors work only because electrons behave exactly as QED predicts. Without QED, engineers would not understand electric current, energy levels, electron movement inside chips. No QED means no smartphones. Computers and microchips. Computer chips function by guiding electrons through microscopic pathways. At this scale, classical physics fails. Only quantum behavior explains why chips work. QED allows engineers to design transistors only a few nanometers wide, thousands of times thinner than a human hair. Modern computing exists because QED tells electrons how to move. Lasers. Lasers are a direct application of QED. They work by controlling how atoms emit photons. The precise interaction between light and matter predicted by QED makes laser light perfectly focused, highly stable, extremely powerful. Without QED, lasers would not exist. Internet and fiber optics. The global internet relies on laser light traveling through fiber optic cables. Every email, video, and message moves as photons guided by quantum laws. Those laws come directly from QED. Light behaves exactly as the theory predicts, allowing information to cross continents in milliseconds. GPS satellites. GPS systems depend on atomic clocks. These clocks operate using quantum transitions inside atoms. Without quantum corrections, GPS would drift by kilometers each day. QED ensures the timing is accurate, allowing your phone to know your exact location. The big truth. From phones and computers to lasers, satellites, and the internet, every technology that uses electricity or light is built on QED. It is not optional, it is fundamental. QED is not just the most accurate theory in science, it is the reason modern civilization functions at all. Without it, the digital world would simply disappear.
Richard Feynman believed quantum electrodynamics was special for one simple reason. Nothing like it had ever existed before in human history. QED was not just another scientific theory, it was the most accurate description of reality humans had ever discovered. First, QED predicts nature with unmatched precision. Its equations agree with experiments to 10 decimal places. No other theory, not relativity, not chemistry, not biology, comes close. For Feynman, this level of accuracy was almost unbelievable. It meant that human mathematics and the universe were giving the same answer. Second, QED explains light and electricity better than any theory ever created. Everything involving photons, electrons, energy, and magnetism follows its rules. Light shining from the sun, electricity flowing through a wire, even atoms bonding together, all obey QED. Third, QED showed that nature itself behaves mathematically. The universe seems to calculate probabilities, explore all possibilities, and then choose an outcome. As Feynman said, it is as if reality is constantly computing. This idea deeply changed how scientists understood existence. Fourth, QED made the modern world possible. Smartphones, computers, lasers, GPS, microchips, and the internet all depend on it. An abstract theory about invisible particles became the foundation of modern civilization. But what impressed Feynman most was this: QED works perfectly, even though no one truly understands why it works. That is why he famously said, "I think I can safely say that nobody understands quantum mechanics." Not because it is wrong, but because it is too accurate, too strange, and too beautiful for the human mind to fully comprehend. For Feynman, QED was not merely a theory. It was a glimpse into the hidden logic of the universe itself, a reminder that reality is far deeper, more precise, and more mysterious than we ever imagined.
I think I can safely say that nobody understands quantum mechanics. At first, it sounds like he's admitting defeat, but that's not the case. It's not that quantum mechanics is wrong, it's that it is too perfect, too precise, and too strange for the human mind to fully grasp. Particles can exist in multiple places at once. They explore countless paths simultaneously. Reality itself behaves probabilistically, not deterministically. Yet, despite all this weirdness, the theory works flawlessly. Experiments confirm it to 10 decimal places. Feynman's point was simple. Quantum mechanics is unimaginably accurate, but its rules stretch far beyond ordinary intuition. In other words, nature is smarter than we are, and that's exactly what makes it so fascinating.